In this video, we're going to see how to draw graphs of those transfer functions we mentioned in the previous video. As we saw, by using our logs, we could break up into the different terms, and we're going to analyze the three most common terms and how they're going to look individually. Then when we go to draw full graphs, we will just combine them by adding the individual results. For the first one, it was just the constant in front of the transfer function, the k there. If you look at the decimal formula for that, just the k, you have 20 log absolute value k. So what that means is no matter what omega is, it's the same value, 20 log 10k. That is a constant, and so our graph, even on the log scaling, is going to be a perfect horizontal line here. So what that means in terms of the overall graph, since we're adding up all of our individual results, the 20 log k is just going to give you a vertical shift up or down by that value on your graph. So the leading factor, the constant, is the easiest one to handle here. It's just going to be completely horizontal. The next one is the linear term by itself, where your h of j omega is just j omega. Then when you go ahead and find your decimal formula for that, you get 20 log of omega. Now, if you drew that on a regular scale, that would absolutely not be a straight line. But in terms of log omega, since we're using a logarithmic scale on the x-axis here, and you can see one hash mark is 0.1, the next hash mark is 10 times that, the next hash mark is 10 times that, the next one would be over 100, and so on. So by doing these scaling on the x-axis, we are using a log scale on the x-axis, which means that this is 20 times just the input variable. So we're going to get this nice straight line whose slope is 20, and the units of that are going to be decibels per decade. So going from 1.0 to 10, by a factor of 10 here, that's called a decade. So the slope is 20 decibels per decade. Now you want to be a little bit careful with these because this is not going to be defined at 0. What would happen with omega is 0 here? You would have 20 log of 0, which is either undefined or negative infinity, depending on who you talk to. So this graph really goes to negative infinity, but you're only going to see a straight line here, which normally doesn't go to that. So what that means is this axis right here, this axis is not actually omega equals 0. It's just some other omega value there. And when we draw it, just understand, just like on top here, this graph, the first line was omega is 0.1. We didn't have this weird asymptote problem on that because it's just constant everywhere. However, we want to just realize that when we're drawing these are called Bode plots, by the way, I should mention that earlier. Drawing these transfer functions on this log scaling, these are Bode plots. And when we're drawing Bode plots, when we draw this y-axis here, just know this is probably the one time ever that you're having a y-axis. It does not mean that the x-axis is 0. So we're not even worried about what specific number it is. All we're worried about is that it's a straight line. It's going to keep going down. And the only way to really center what's going on here is by picking 1 at this point, because what happens if you plug in 1 to this, 20 log of absolute value of 1, well, log of 1 is 0, so we know that the x-intercept is going to happen at 1 there, and that's the reason why we choose that point. So just remember, anytime you have a factor of j omega, it's just going to be a nice straight line going on forever at the slope of 20 decibels per decade. And if you had something like h of j omega is j omega squared, well, when you do your logs, it's just adding up 2 of these things here. And what's going to end up just happening is it's going to take this and make it a higher slope. In that case, your slope would be 40 decibels per decade. So whenever you have a higher power of just j omega by itself, it's just going to change the slope in multiples of 20. And if you have your h of j omega on the bottom here, so h of j omega is 1 over j omega. It's still going to be a straight line, but in that case, your slope is negative 20 decibels per decade. So that's the only difference is when you have powers of j omega. Now I want to point out, this is not when you have a whole j omega squared plus 5j omega plus 2. It's not when you have a polynomial. It's when you have just a single term, j omega to a power, that we saw we factored out in front of the transfer function. Now the third case that we're going to worry about, it's actually going to be the most common case that we're going to deal with. It's going to be several in a given problem. It's when we write it in the form 1 plus j omega over z naught, z1. Which means the decibels then is 20 log, and if you do the magnitude of that, it's going to be, well, square root, I guess, square root of 1 plus omega squared over z1 squared. So let's take a look at this term here, 1 plus omega squared over z1 squared. Well, there's going to be two kind of possibilities that we're going to look at. If your omega is smaller than z1, and we're going to use this special notation where it's like a double less than sign, which means omega is much smaller than z1, then if you divide them, omega over z1 squared is going to be much less than 1, essentially 0 in this case, then what your term is going to be 1 plus omega squared over z squared is going to be basically just 1, and you'd have 20 log of 1 is 0. So that's why in my graph it starts out being just flat with a value of 0. However, if your omega is a much bigger number than your z1, then omega over z1 squared is going to be much bigger than 1. And what that means is, if it's much bigger than 1, then adding 1 to it doesn't really change things. Like if you have $1 billion in the bank and you add $1 to it, you're not going to notice that. So this is going to be pretty much the same as just omega squared over z1 squared. And when you do this, it's just going to be 20 log of omega minus 20 log of z1. This is just going to be a straight line whose slope is 20 decibels per decade, and whose y-intercept would be this negative 20 log z1 here. And so since we have these two parts here, we're just going to say starts out flat. Once it reaches z1, it becomes this straight line slope, and that's what you're going to use. It's called the straight line approximation. Now it's a little hard to see. Let me erase what I've done here. And you can see here is that the flat lines is our straight line approximation. There is a problem here, because what if omega is around z1? Not much smaller or not much bigger. What if it's near z1? Or what if it's even exactly z1? Well, that's this extra line here. It's the exact graph of what's going on. Because it's hard to try to do that manually without computer help, I'm not going to be making you draw this exact graph by hand. We're going to stick with the straight line approximations, and that's what we're going to do here. So what you should know is anytime you have these terms, 1 plus j omega over a z value, the way we're going to do that is going to start out flat, and then once you get to z1, it's going to shoot up at a positive 20 slope, and it's going to continue on that forever. On the other hand, if you happen to be dividing by one of these terms, it's going to start out flat and then shoot down at a negative 20 slope. So you want to know these three cases, and we're going to see later videos how to combine them together to draw an overall Bode plot.